Hello, everybody, and welcome back to this collection of short videos on getting started with the Julia programming language. Today, we're going to be diving right in and introducing some of the core concepts of Julia. As a scientific computing programming language, we're going to start where it probably makes sense with the foundational building block of scientific computing, or numbers. What are they and how do we represent them in a computer? All right, so let's just dive right in. I'm going to go ahead and boot up the Julia REPL. I'm not going to cover how to install Julia. It's pretty straightforward. Just go to the documentation online. All right, so I'm going to be working with the REPL, or the interactive version of Julia. And let's just start with how to define a simple variable. So let's say we have a variable A, we just use the equal assignment, and boom, we have a variable with an integer value of 1. Now, if we want to check the type of that variable, we can use the type of command, and we can see that by default, Julia is giving us a 64-bit signed integer. So as you would expect from a scientific computing language, Julia comes with a whole suite of both signed and unsigned integer types, all the way from 8 bits all the way up to 128 bits. So if I want to create any of those types, I'll just cast a integer literal with the type that I want. So for example, if I want to assign an unsigned integer of 16 bits of like 123, I can do that and just sanity check ourselves. We can check the type of that, and we can see that it is indeed an unsigned integer of 16 bits. So in addition to this, Julia also allows us to directly declare unsigned integers in a couple of ways. We can do hexadecimal, octal, as well as binary. Now, the cool thing about these, if we check the type of these constants, you'll see that the accuracy automatically grows with the size of the literal that I am typing out, all the way up to, like I said, a couple more, 128 bits. So that's a nice shortcut. In addition, Julia also gives us a couple extra features for working with these types. We can do type max of int 64, and we will get the maximum representable integer. And these also obey wraparound. So if I check the type, if I add 1 to the type max, I should get the type min of the same type. And we can see that that is true. All right, that's pretty much it with integers. Moving on to floating point numbers, Julia has half, single, and double precision, which we represent as float 16, 32, and 64. Pretty much don't use float 16. It's represented on the hardware as a float 32 anyways, so it's just going to be more expensive and not going to save you any performance or memory space. By default, Julia will, all decimal literals are going to be 64-bit floating point numbers. So pretty much everything in Julia by default will be 64 bits, or double precision arithmetic. Now, if you want to create a single precision arithmetic number, you can use the F construct, and I can see that this is type of is a single precision. So the F also works as an exponential. So if I can do F to the 10, the corresponding double is going to be 1e to the 10. Again, these are just shortcuts for declaring these either way. You can always just explicitly type float 32 of a particular decimal number, and it will give you a 32-bit float. Type max and type min also work on these, and as expected, they're going to give us positive and negative infinity. We also have a nan literal for not a number, and all of these obey the IEEE rules for infinite and not a number values in terms of arithmetic and logical comparisons. In addition, Julia also throws us a couple extra features for working with floating point numbers. We can use the epsilon command to give us the machine precision. We can also pass in float 32 to get the 32-bit machine precision representation. We can also do, using operator overloading or multiple dispatch, we can also pass in a floating point value or number, and we can see that this will give us the distance between that number and the next representable integer floating point number, using the precision of the type that we passed in. So if I instead did F to the 10, you'll see that it's a pretty big difference in the precision of those all the way out at the with a power of 10. We also have one extra kind of nifty trick here. So if we add this to 1e to the 10, like I said, we're going to get the next representable float. And here we can short this with next float of 1e to the 10. We also have pre-float, which is the companion and just going the opposite direction. And again, these are handy to have if you're like in the weeds of doing numerical comparisons. But if you don't want to be like that in the weeds, Julia also simplifies this problem for us of like comparing similar numerical values when it comes to floating point numbers. So I want to check if 1e to the 10 is approximately equal to another value. I can always do this. I can do the approximately equal to symbol, or use the isApprox command. So here I typed in a question mark in the REPL, and that's going to open up the docstring for the method that I type next. And you can see that this pops up the documentation for isApprox. And here I have the option to provide absolute and relative tolerances. I'll cover the syntax of how to like pass in these keyword arguments later, but just know that you can access the documentation right there from the command line in the REPL. One last thing that Julia kind of does nice for us when it comes to numbers and precision. We have a couple of numerical literals called irrational numbers, such as pi. So we can represent pi either with pi or with the Unicode character pi. And if we check the type of this, we're going to get something interesting. You see that this is actually an irrational type. Now what this does is it basically matches the precision of the surrounding operator. So here I'm going to do a floating point, a double precision. And if I multiply this by pi, I'm going to get a double precision result. But if instead I do single precision, you're going to see that pi matches the single precision of the number that I'm multiplying with it. So that's just like a nice thing. We don't have to have two versions of pi. We can just have one, and using the power of multiple dispatch, it'll automatically pick the right precision for us. All right, that's a couple of the introductory ideas of Julia and numerical values, and also like a small introduction to the type system within Julia and how types themselves are also like functions and actually also objects that we can pass into other functions, as you've already seen today. All right, hopefully that gets you started. Go ahead, download Julia, try out some of these things, and I will catch you on the next video. See ya.